So the topic in this learning cycle is Monte Carlo and Bootstrap methods. And in this first video in the topic, I just want to give you an overview, a brief introduction to what this is all about. The general idea of Monte Carlo and Bootstrap methods is to use a computer to simulate building a sampling distribution of a statistic. We can then study this sampling distribution to better understand the properties of a statistic, as well as to make inferences, that's usually in the form of confidence intervals, about the parameter that the statistic estimates. So when you hear Monte Carlo methods, it means that you're going to be involved in simulation. You know that the sampling distribution is really the crux of all statistical inference, as I'll discuss more in a moment. And so we're using simulation to do inferences via the sampling distribution. A little bit of history. The term Monte Carlo that we use for simulation methods actually originated as a code name for simulations in the secret Manhattan Project when they were building the first atomic bomb. These simulations were used to anticipate rates of fission in an atomic bomb. They had never created such a bomb before, obviously, and so they didn't know exactly what would happen. So they made a variety of simulations to see if they could project what the power of the bomb might be, what the range would be of the explosive device, and so on. And as in any secret project, when you have different elements or subsets of that project, you might need different code names for it, not to give away what you're doing. They were searching for a code name for this one, and true story, one of the scientists at Los Alamos said that he had an uncle who would frequently gamble in Monte Carlo, and due to that gambling would end up asking the family for money, and was always asking the family for money because of his Monte Carlo gambling. And since they were doing simulations that were based upon randomization, just as we will be doing, they decided that they would call these Monte Carlo studies. And so that name has stuck. We still use it today. And when we do statistical inference or any kind of simulation study in statistics, we call it a Monte Carlo study. Now that is a broad term referencing any kind of simulation. And Bootstrap, which I gave as one of the parts of the title, I called this Bootstrap, or rather Monte Carlo and Bootstrap methods. Bootstrap is also simulation, so really it can be thought of as a Monte Carlo method. But it's more common to reference it with the more specific term bootstrap because of the unique characteristics of that type of simulation. So I just want you to be aware that when we talk about Monte Carlo and bootstrapping is really a special type of Monte Carlo. And in terms of the language of statistics, when researchers say they're doing a Monte Carlo study, they usually mean a simulation study other than Bootstrap. And when they're doing a Bootstrap study, they usually mean that they always mean that they are conducting a study that involves a particular type of simulation, which we call a bootstrap. So Monte Carlo is the overarching term, but we really use Monte Carlo and Bootstrap almost like they're two separate methods. And so that's the way I'm going to be doing it throughout these lessons. Let's talk about the purposes of each, starting with Monte Carlo. One of the primary purposes of Monte Carlo methods in statistics is to explore the properties of statistics. For example, we might explore how robust the t-test is if we violate some of the conditions for valid inference. What about if, for instance, our units that we're analyzing are not independent of each other, but dependent on each other? How will that influence the type 1 error rate? How will that influence the power? What about if we have a skewed distribution instead of a normal distribution? How big of a sample size are we going to need before the sampling distribution is normal? That will probably depend upon the amount of skewness, so we can study that. We can vary the amount of skewness in our simulation and see what happens to the distribution that we get of a sample the distribution we get of a sample statistics, such as the mean, and see if the sampling distribution becomes normal for certain sample sizes. That helps us understand how big of a sample size do you actually need in order to be able to hold your type 1 error rate. So we're really playing as though we know the population and we're simulating drawing samples to see what will happen as a result of that. And through that, we can explore the properties of statistics. Monte Carlo is used in a special way as well in non-parametric methods, and that is to make inferences when exact values are not possible. You already know one way to do that, and that is through large sample approximations that rely on the central limit theorem. But there's another way to be able to estimate such things as p-statistics without doing a large sample approximation, with still doing an exact test, even when there are too many different randomizations, too many different ways in which we can randomize the data for us to actually see it as feasible to do it. You know that when we do such things as the Wilcoxon sign rank test or at Fisher's test with original scores, that if we have too big of a sample size, and too big can only mean maybe 20 or 25 or 30, that the number of possibilities becomes so large, the number of permutations becomes so large that we really can't create that exact distribution. And when that happens, we can either switch to a large sample approximation and rely on the central limit theorem, or we can use a Monte Carlo method that I'll show you in order to find out what the p-statistic value is. And that p-statistic value using Monte Carlo methods, especially if we use large enough Monte Carlo methods, will be almost the same as the exact value. So it's a way to keep doing an exact test that is kind of exact with quotes around it. It's not truly completely exact because we do use some simulation and not doing the whole distribution when we're looking at the p-value. But it's also not a large sample approximation. So in some ways it could be preferred to a large sample approximation, though eventually these tend to all converge on the same values. Bootstrap has a similar purpose, that is to make inferences. That's why we do Bootstrap, to make inferences. And I'm going to explain more about how that happens in a later video when we specifically look at Bootstrap. But in essence, what we're doing is using our observations to be able to make some guesses about what the population might look like. And there are two primary kinds of Bootstrap, just like there are two primary kinds of statistics, parametric and non-parametric. There is parametric bootstrapping and non-parametric. I'm actually going to talk to you about both. You might wonder, why am I talking about parametric bootstrapping in a non-parametrics course? And the answer to that is that we teach at this university, at least in my program, we teach Monte Carlo methods and bootstrapping in the non-parametrics course. You will never learn about parametric bootstrapping in any of our other parametric statistics courses. So even though this is a non-parametric course, Bootstrap sort of falls under the categorization of non-parametric methods. And so I'm going to teach both parametric and non-parametric bootstrapping to you. And you'll see why the parametric bootstrap sounds a little bit like nonparametrics and a little bit like parametrics. It's kind of a combination of the two. And you'll also see why nonparametric bootstrapping sounds very much just like nonparametric statistics. So that's probably what you'll end up doing most of the time. But I want you to be familiar with both terms because you're going to hear about bootstrapping as parametric or non-parametric. And when you use bootstrapping, people are going to want to know, did you use a parametric bootstrap or a non-parametric bootstrap and why? Now, all of these methods, both Monte Carlo and bootstrapping, as well as all of statistical inference in general, relies on sampling distributions. So real quickly, I think this is probably unnecessary, this review, that you probably all know about sampling distributions, but just in case, and because it doesn't hurt to review something that is fundamental to statistical inference, let's do a short little review of sampling distributions. So we begin with a population. So we have a population that we draw a sample from. We might not know what the population looks like. We may have ideas what the population looks like. Those ideas could come from many past research studies, or they could come from our theories about what our measures do and how they perform within a population. But regardless, we cannot see that population. All we can see is a small, relatively small number of observations. We call that N, our sample size. Those are the observations. And so we draw from that population, preferably at random, because that's what allows us to calculate real probabilities. Otherwise, they're very rough estimates. We calculate these probabilities based upon making a random sampling of N observations. Now, a sampling distribution can be thought of as a thought experiment. It's an idea. It's not something we actually do. But the idea is this. Imagine if you were to take another sample, you would get a different sample. You would be making different observations if you took another sample from the population. And if you took a third sample from a population, you would be making even more. You'd see even other differences. You'd have 3 different samples with 3 different statistics because the samples are all different. So if we were to, for instance, calculate the mean for the first sample, it would be different or likely to be different than the mean of the second sample and the third. If we were going to do this with the median, same thing. So we keep doing this over and over again. Remember, this is a thought experiment. We don't actually do this in research. We keep doing this over and over again. We keep drawing sample after sample after sample after sample after sample in our minds from the population. And we calculate a statistic such as a mean or a median from each sample. The distribution of all these statistics is the sampling distribution, and we use this sampling distribution to make our inferences. And so when you learned parametric statistics, we talk about sampling distributions a lot in parametric statistics, but we do it relying on the central limit theorem. So we say we have a population, and imagine if you were to draw many samples from that population, each of size n, and then calculate the mean for each sample. That's usually where we start, is with the mean. We can go to other statistics, but we start with the mean. Calculate the mean for each sample and look at the distribution of that sample. Well, it can be mathematically proved that that distribution, when n is big enough, that distribution will be close to a normal distribution, and the bigger n is, the closer that sampling distribution will be to a normal distribution. It's what allows us to do tests like the t-test, even when the population distribution is not normal, because the t-test is based not on the population, but on the sampling distribution. And so if that sampling distribution is normally distributed, we can hold the type 1 error rate. Now, you know from what we've done already in nonparametric statistics that if we have a population that is not normally distributed, that even though the sampling distribution will be normally distributed and we can do a t-test and we can hold type 1 error, that it may not be the most powerful thing to do, that there may be other statistics that we can use based upon other than the mean or other than the original scores, some transformations we could use in order to be able to obtain a sampling distribution of a different test statistic, such as the sum of ranks, that might actually allow us to test the median or the mean in a symmetrical distribution with more power than we would with the t-test. But when you first learn statistics with the t-test, you're learning about the central limit theorem as assuring us that the sampling distribution is normal. So that's why I say the sampling distribution is really the root of inference. And that's true in nonparametric methods as well. It's just we look at different sampling distributions, not just the sampling distribution of the mean, but the sampling distribution of, say, the sum of ranks or the sum of normal scores or the sampling distribution of the number of successes that one gets. So those are all different sampling distributions that we've looked at. We have not often to this point used the term sampling distribution, but that's what we're looking at every time we do a inferential test. So we can have multiple ways to calculate sampling distributions, but before there were computers, there was only one way. And that was you assume the population distribution can be represented by a function that describes a mathematical form, and then you mathematically derive the sampling distribution. So when I said we were doing a thought experiment, we can actually turn that into a mathematical derivation based on that thought experiment. And that's what mathematical statisticians have done. And they're the ones that have been able to tell us, hey, look, if you're getting multiple samples, in fact, thousands and thousands and thousands of samples, and you're calculating the mean for each, we can actually mathematically prove that those means will be normally distributed as long as your sample size is big enough, no matter what the underlying population distribution. And we can prove that the average of all those means is actually going to be the mean of the population. That is, the mean is unbiased as a statistic. And we can prove that the bigger the sample you take, the narrower your sampling distribution will be. The narrower it will be, the less variance it will be, meaning that because of the law of large numbers, it will converge on the actual true mean of the population with bigger and bigger samples. In other words, we're saying that the mean is a consistent estimator. So the mean is unbiased, it's consistent, and the sampling distribution of the mean is normal as long as we have a big enough sample size. So that's how we did sampling distributions. It was all mathematical. With computers, we could take any population distribution and describe it. We don't have to assume a certain mathematical form. We can say, what if we have a population distribution that is leptokurtic in a certain way or platykurtic? What if we have a distribution that is like a mathematical distribution, say normal or uniform or logistic? We can describe either with a mathematical formula or just describe it in other ways, a population distribution. And here's what we can do with computers. We can actually simulate that we're sampling from that distribution. If you've ever used the rnorm function in R, and maybe some of you have not because you're new to R, but in R there's an rnorm function, and that rnorm stands for random sampling from the normal distribution. So you can specify the mean, you can specify the standard deviation of the normal distribution, and you can say, hey, R-norm, give me 100 samples from that distribution. What are you doing? You're not actually going to some population and taking a sample of participants and measuring them. You're simulating as though you did that. And if you simulated that over and over and over and over again and calculated a statistic for each of those samples and then looked at the distribution of the statistic, you'd be looking at an empirically built sampling distribution. So with computers, we can empirically build a sampling distribution. Another thing that we can do with computers is look at an actual sample that we have and go in the other direction. Instead of simulating drawing a sample from a population, we can actually simulate the population from the sample. And we can empirically build the sampling distribution from the sample because we're simulating the population. So it's two different ways of doing it. One, start with the population and build a sampling distribution. The other is to start with the sample and build, as it were, a population, but actually we skip right over to the sampling distribution from the population. The first of these is fitting into what I would call Monte Carlo. The second of these is the method of bootstrapping. And so even though all of these are simulation and therefore Monte Carlo, we would call the first one a Monte Carlo simulation and the second one bootstrapping. Seeing the future. This is becoming bigger and bigger and bigger. It is being integrated now into statistics courses like never before. And it may be that someday in the future, we won't teach statistics the way we do now, starting with parametric distributions. For years, statistical inference has been based on mathematical models and mathematically derived properties of sampling distributions. But now we have the capability to derive empirical sampling distributions on our personal computers. And because of that capability, we can actually create inference from empirical simulation. The strength and beauty of mathematically proved theorems will always provide a solid foundation for inference, yet empirical inference adds flexibility. Here's why. Because if you specify what you believe in your particular context, you can then empirically generate sampling distributions, study them, and then from those sampling distributions, make inferences that are specific to your context. You can use empirical inference to check the robustness of methods. So you may say, look, I have a situation here where I have a skewed distribution, or maybe I have a normal distribution with slightly heavier tails than normal, but it's not quite logistic. Or here I have a distribution that's not really Laplace, but it's kind of heading that way. You could set up a situation where you then compare various methods to see which ones have more power, or you might take the parametric method like a t-test and say, will the t-test hold the type 1 error rate in my situation, or am I safe in using it? So you can check the robustness of methods. And then, as we're going to be doing here in one of the videos coming up pretty soon in this learning cycle, is we're going to see how we can approximate quantiles of exact methods without resorting to large sample inference. And we can estimate populations from samples, the bootstrapping method. So all of these fall under empirical inference, and it very well may be the wave of the future, as indicated by the image on this textbook, this wave, and the textbook's entitled Computer Age Statistical Inference. The first author of that textbook, Bradley Efron, he invented bootstrapping. And he and his co-author in this book, which by the way is available as a PDF for free, if you Google on Brad Efron and computer age statistical inference, you can go to a site where you can download the PDF. Yes, you can buy the book as a paperback book, but you can download the PDF for free. And one of the arguments that these authors make in this book is that the future is going to see more and more empirical inference and less of the mathematically derived inference, because now we can do it. We couldn't do it once upon a time. We could not, back when statistics was first invented, and inferential statistics specifically, when Ronald Fisher was working on his inference, he's the first one that came up with the idea of the exact test that we're using here so far in our nonparametric methods, but he didn't use it because he didn't have the computing power to be able to do it. So instead, he was right along with the other statisticians of his age that were doing mathematical computations to be able to make approximate inferences based upon mathematical models. We can now actually use empirical data to do our inferences. Pretty cool, I think, and I hope you think so too. If we come back in 10 years and we take a Stats 101 course, or the course I teach, Educational Statistics 1, that course may look different. Obviously, we have a lot of inertia, and inertia tends to be really powerful. And I would be a little bit pessimistic about how fast we're going to move into this new era, simply because we have to outgrow the generation of statistics teachers who this is what they learned and all they learned.